So this problem is going to be based on a force applied to two blocks. And one thing that we're going to look at is first a situation without friction, then we'll look at a situation with friction. The nice thing about this problem is you can do the same thing with multiple blocks, or you could do it with strings in between each object. So first, I might ask, what is an expression for the acceleration? Well, for that, I would just use the sum of the forces for the system equals ma, and m in this case is 3m. And the sum of the forces is just F. So F equals 3ma, so F over 3m equals A. And in this situation, you could draw also an individual free body diagram for each piece. So if I call this block A, call this block B, I'd see that diagram for A has mg, in fact it's 2mg, so this would be the normal force of size 2mg. Then there would be a force applied to it, F, but there's also a force going back on it from m. That's also a normal force. Which is the size, if I look at the other free body diagram, it's the size of the normal force that's pushing this block from the other block, block A. So I'll say this is normal force from A to B. I'll call this the normal force from B to A. So now, let's say I want to find the force, the net force on this object. Well, what would I have to do? Well, I know its acceleration. The acceleration is F over 3m. And I know its mass, which is 2m. So we multiply by that by the acceleration to get the net force, which in this case is just m is canceled, 2/3 of the force on the entire system. Likewise, we can see that for B, we have a mass of m, an acceleration of F over 3m, so the sum of the forces on B would happen to be, this is in the x direction, because the vertical and horizontal, or the verticals cancel out, or balance out. In this case, it'd be m times F over 3m, because both objects are accelerating at the same rate, and we get that to be the sum of the forces, which is the same as just saying F over 3, or 1/3 of the total force. Now, in this case, you'd say, okay, well, what is that? That is, in fact, this force here. whereas this is the applied force of F minus the normal force back of 1/3 F. So this is equivalent to F minus the sum of the forces on B reflected back onto A as a normal force. So that'd be minus F over 3, which is equal to my 2/3 F. So I can look at the contact force here, and I can see that that happens to be exactly the force that's propelling B forward. And it's the force that balances partially with the initial force on A, so that instead of the acceleration being F over 2m, the acceleration is F over 3m. Okay, let's see an example with friction. So I'll make a new layer here. Close that off. Let's see a different situation. This time we still have F applied, but we also have those coefficients of friction. So we have a couple situations. This is situation 2 with friction. And what I'd say is that, to start out, I'll say, what is the maximum value of F that keeps these in place? So, well, first, let's think about this system. We have, if we think of this as a system of 3m, of size 3m, I have down a normal force, or a gravitational force of 3 mg. I have up a normal force of 3 mg. I have to the right my applied force, F. I have to the back my frictional force, which is equal to mu s times 3 mg, which is the same as mu s times my normal force. So really what I'm looking for is a situation where I know my vertical forces are balanced, so the sum of my forces in my y direction is 0, which is just mg, 3mg equals the normal force. And I know that the sum of my forces in my x direction is the left force, is the right force subtracting the left force, which in equilibrium would set to 0. So we know it's 0. So that's force to the right, the applied force equals the frictional force, which is mu s times 3 mg. And so that would be the limiting factor. That's the maximum value of friction, or of the applied force, to keep this stationary. Now the question is, how could I find the coefficient of friction? Well, that's easy enough. I divide each side by 3 mg. So the applied force over 3 mg is my value for the coefficient of friction. Okay, so the units here would cancel out. I get 1/3 here as some coefficient. So let's see what we can do in terms of the forces on each individual block. This is for my 2m, mass A. And I'd say that we have 2 mg down. I'd say we have, therefore, my normal force up. I have my applied force to the right. I have my frictional force back plus another force back, my normal force from M. Likewise, if I look at B, mg down, Fn up, I have my applied force going forward, and I have a frictional force going back. So the question is, what is the net force here? Well, let's start with B this time. So the sum of the forces on B, the x direction, because the y direction cancels out, is going to equal, in this case, 0, because we're assuming we're in static equilibrium. So in this case, I'd say 0, which is equal to my applied force, which we don't know yet. It's some normal force, equal to my frictional force. So my frictional force Fn from A to B. My frictional force in this case is what? The maximum value would be mu s times mg. And that has to equal the force going forward, which is Fn. So that's the force right there going forward is just going to be equal to my Fn from A to B. Likewise, this also has to be the value of that normal force. So going to the left for A, we have this frictional force plus that friction, this normal force plus the frictional force there on block A. The normal force plus the frictional force and that's going to equal my applied force from the left, or going toward the right, that I apply right here. And that's because we're in equilibrium. So, in this case, I have this situation I want to solve, so I know that my normal force from B to A has to be mu s mg. I know my frictional force on the block 2m is mu s times 2 mg, the normal force on the object, and that has to equal my applied force. So in that case, and this is the result we got from the beginning. So if we want to know the applied force there, it's mu s plus 3 mg. If we want to know the frictional force on the object, it has to be mu s plus mu s 2 mg, because that balances with the force backwards from m to cancel out the force forward. If we're talking about an acceleration, however, the problem changes entirely, because we have to account for the idea that friction plus the normal force back from B to A which is subtracted from my force applied is equal to the m times the acceleration, or in this case 2ma for that first block, or 3ma for the system. So we have to account for more forces when finding an acceleration. Or we have to rearrange how we have them interact. They don't just balance each other out. They add to create a net force. Okay, let's do one more problem. Okay, so let's say I have an inclined plane, angle theta, and I have a block here, and I'll just say that's m, and hanging off I have a block of mass 2m. And I want to know the theta at which these hang in equilibrium. And how do we do this? Well, we might say that let's draw a free body diagram first. So for block A versus block B, we have free body diagram, we have mg down, we have the normal force out from the surface, and to start out we'll say there's no friction, so the only force this way is tension. Likewise for object B, mg down, 2mg down, we have tension up. So if we have some acceleration that is 0, then 2mg is going to equal tension on this side, because the sum of the forces for this block would be 0. So the up force would equal the down force. Likewise, if I know that t can be represented with 2mg, this object, well, we have mg down, we have components where this component is mg cosine theta, and this component is mg sine theta. So the down the ramp value is mg sine theta. Some of the forces in the y direction would be Fn is mg cosine theta. The sum of the forces in the x direction would be mg sine theta minus tension equals 0. Therefore, mg sine theta is tension, is equal to the tension value, and if I have this and I substitute it in, I get mg sine theta equals 2mg. The mg's cancel. I get sine theta equals 2. So the inverse sine 2 equals theta. Now, what is the problem with that? Well, that's not a valid value. So what does that tell us? That tells us that there is no situation here where I'm going to be able to get equilibrium with 2m pulling down and m pulling this way. So the situation where equilibrium is possible would be a situation where we have m1 here, and m2 here, and we want to see the ratio of the masses for which equilibrium is possible at any angle theta. And the answer would be that m1 sine theta, m1g sine theta, has to equal m2g. Therefore, m1 sine theta equals m2. And the angle at which that's possible here would be the inverse sine of m1 over m2. So any angle we have a valid value for m1 over m2, the inverse sine of that gives us our angle. So any angle that we can get from this function will be valid for the ratio of masses here. Now, let's see a slightly different problem. Let's look at it with friction. So here, let's see a situation where we have an m value here, and a 2m value here, and we want to know that this is not in equilibrium, and I want to know the acceleration. And how do I find the acceleration? Well, first condition is that there is friction, mu k value for friction. And two, I want to get to my free body diagram. So for m, I have mg down, I have Fn this way, I have tension this way, and I have friction going down the ramp. And likewise, for this one, 2mg down, and tension up. So for this situation, I have the sum of my forces equals ma, 2ma really, which equals 2mg minus whatever my tension value is. For this object, I have the sum of my forces is equal to, well, we know the mg down, mg cosine theta, opposed to my normal force, mg sine theta goes down the ramp. And so I know I have mg sine theta down the ramp. And because I'm sliding up, I know my friction value also has to be down the ramp. So in this case, I have mg cosine theta times mu k for my friction value. So down the ramp, I have mg sine theta. I know I also have mg cosine theta times mu k. That's my down. But I also have to subtract that from the tension, which is up the ramp. And that's going to equal the ma value that I have for its acceleration times its mass. That's the net force there. So here, if I have t minus mg sine theta plus mu k mg cosine theta, that equals ma. And I have the other problem here, where I have 2mg minus t equals 2ma. And I add these together. I get 2mg minus mg sine theta plus mu k mg cosine theta equals 3ma. And so what are we looking for? We're looking for the acceleration. Well, in that case, I would just divide each side by 3m. And I'd get m's that cancel across. So I get 2g minus g sine theta plus mu k g cosine theta over 3 to equal my acceleration. Not a very satisfying value. You'll notice that here I can pull a g out. So I get g times 2 minus sine theta plus mu k cosine theta over 3. And that is my acceleration. So a complicated situation leads to a weird acceleration that's dependent on the angle, coefficient of friction, and the ratio of the masses to some extent. Now, this would be a slightly different form if I, instead of having a discrete mass ratio, I had an M1 and M2. But we're going to not, I'll leave that problem to you. If you wanted to solve for mu k here, that's not difficult either. We just have to do some algebraic rearrangement. So if I take this back to its original form, where I get 3ma on one side equal to 2mg minus mg sine theta plus mu k mg cosine theta. I'll subtract this from each side. Let's see if I can copy this. Okay, take that, make a new layer. And we'll drag this up here. And so what we'll say is that with this problem, I get 3ma minus 2mg equals negative mg sine theta minus mu k mg cosine theta. Again, m can cancel out of here. I'll take it out later. Add this to each side. Divide each side by negative mg cosine theta. And we get negative 3a minus 2g plus 2g minus g sine theta over g cosine theta equals my mu k value. So it's just algebraic isolation there. And I'm sure there's probably a way to clean this up a little bit, but for the most part, it's going to be a messy expression determining the mu k for some acceleration in the circumstance of an object of size m versus 2m falling down the ramp. Just as a reference. So, general steps, free body diagram, sum of your forces, both x and y, and for each object. And then solve for desired variable. You can always plug in values here. So you can see that the mu k doesn't depend on mass. Okay, thanks.